This is the code by DeepSeek, so the V3 model, that lets them convert their numbers from floating point 32 or floating point 16 to floating point 8, making the memory requirement 4 times or 2 times smaller. And they use that to store their numbers, their matrices, their arrays and tensors in the memory and to move them around. And then they will do matrix multiplications in FP32 format for maximum precision. So they will use FP8 to move numbers to move around the arrays to reduce the memory bandwidth necessary and computations will be done by first converting to FP32 and then calculating for maximum precision. Later, I will accidentally mention that computations are done in FP8, but that's a mistake. They are done in FP32, but the memory saving and memory moving around is done in FP8. So this is the quantized form of the number they are using. Right now it looks like gibberish, but I will explain. So the command is torch.float8, representing 8 bits to save this number, quantized number. And exponent, 4 bits in the exponent, 3 bits in mantissa. It's 1 bit for the sign, as always, and then this fn means finite only, or it cannot represent nonce. Now, what is mantissa and what is exponent? So if we scroll down, we see we got 1 bit for sign, so it determines if it's a positive or negative number. 4 for exponent, 3 for mantissa. Naturally, if this was 16-bit model, then you would have more bits for exponent and mantissa, which would let you present more accurately the number. But this saves memory, and this lower precision is good for matrix multiplication in it's precise enough for the models, LLMs like DeepSeek V3. If we have a decimal number 1.5, how do we represent it in FP8? So first we will convert this decimal number to a binary number, and you can search on YouTube how to do this. So 1.5 decimal is equal to 1.1 in binary. After we have 1.1, we need to normalize this number. So what does that mean? If we have any kind of number like 0, like this, point something, we need to move this dot just so it's here before the first one, like this. And the number of places we move this dot, we're gonna multiply with the 2 to the power of 4 here. If we move dot by 4 places, then this is gonna be x2 to the power of 4. But since we didn't move dot, we already have it as 1 dot something, so we don't need to move it. So we will multiply by 2 to the power of 0 because we didn't move it. So this is our number that we will represent in our FP8 format. So exponent is gonna be this number here. You need to remember, the only thing we need to represent is this exponent. That can change. So this 2 to the power will always be the same. We don't need to actually save that into memory, just this number. And also whatever is here behind the dot. So that's gonna change behind the dot. We need to save that into memory. And this 1 point, this will always be the same, because we will always represent the number in this format. So we don't need to change that. So we will change this 0, save this 0 as exponent, and this 0.1 or whatever is here as mantissa. So for exponent, we have 4 bits to represent this number. So we can represent numbers from 0 to 15, because number binary 0 is 0, 0, 0, 0 to the maximum number 1, 1, 1, 1, which is 15. But instead of representing numbers from 0 to 15, it turns out it's better to represent from -7 to 7. So usually this allows, because usually we will have these exponents and not from 0 to 15. So we will use 0, 0, 0, 0 to represent -7, not 0, and 1, 1, 1, 1 to represent exponent 7, not 15. So that means if we want to represent number 0, we will shift it by 7, because now everything is shifted by 7. So now number 0 will be actually 7. So 0, 1, 1, 1. So this will be our exponent. And that's how we are able to present numbers from -7 to 7. And those are more useful to represent than from 0 to 15. I got some more examples, but you can just ask ChatGPT or whatever AI to show you how to represent these numbers in FP8. And you can have a discussion with it and ask more questions. Now let's see how the quantization is implemented. Let's say we have a tensor of numbers. First, we will divide the big tensors that can contain hundreds of thousands of elements of numbers into 128 size blocks. So blocks of 128 numbers. So when we scale them, we are doing it more granularly, more locally, because if we try to scale entire tensor of 7,000 elements, it could happen that scale is too small or too big, so big values get clipped or too small values don't get represented precisely. So that could still happen in 128 size blocks, but it's less likely. Let's see how it's implemented by DeepSeek. So we have some tensor, and it usually has hundreds or thousands of values elements. And then the first thing we should know is maximum number FP8 can represent is about 448. So if one of these values is 1000 and the other is, let's say, 220, we need to scale these values. So the 1000, the biggest number, becomes 448, and then whatever this scaling is, we need to scale the other numbers as well, so that the numbers stay relative to each other. So we divided this big number 1000 by more than half, so by 2.15, for example. Then we also need to divide this number by 2.15, so maybe we get 103 to keep the scale. So now we will represent these numbers. We will scale them down so they fit the so we can represent an FP8. And also, if we have small numbers like 2 and 0.001, we will actually make this number big to 400. So we will convert this number to the biggest number. So this way we can exert or extract more precision. So now there is more difference between them. Maybe this will be 0.05 or something. I'm not sure exactly here, but you get the point. So now there is more difference between these numbers than these numbers. So it's easier to, so now their differences are easier to spot and they are stronger. So this is what we want to do. We want to use maximum range that we can represent, so the difference between numbers become more meaningful and more exaggerated. So let's get back to our first example. So we have the biggest, larger number, 1000. We need to divide it to scale it down to 448. So the biggest number should be 448. So first, we will calculate this scale. So by how much should we scale this down? So here, we will take the maximum but absolute value. So if this was -1000, we would still take this this 1000 as because its absolute value is the highest. Because in FP8 we can represent values between minus 448 and plus 448. So that's the largest negative value we can represent. So we can represent positive or negative, it doesn't matter. So we will just see which value is the largest by checking the absolute value. And then you take so absolute value of the entire block and taking the maximum value. And the reason I say block and not tensor, because I said we have a tensor array of numbers. So why am I mentioning blocks? Because in DeepSeek model, these arrays or tensors can be 7,000 even numbers long. So we could have a wide variety of numbers. For example, we could have one huge number and then a bunch of very small numbers. So if we try to scale this, then this would not be good, because this huge number, this would get messed up because the difference is too much. So either big numbers can get clipped, or the small numbers wouldn't get represented so precisely, the difference between them. So we try to group to reduce chances of this happening. We want to have as even distribution of numbers as possible. So instead of using the whole 7,000 long array, we will put it into blocks of 128 numbers. And then we will scale each block of 128 numbers, which even if the values get a little bit clipped, the scale is not the best, or there is some huge number that messes up the scale, it only ruins this small block. It doesn't even ruin, it just makes it a bit less precise, but it doesn't affect the other blocks. Guys, just a bit of a mistake I later mentioned in the video. I say that computations are done in FP8, but that's not true. The computations are done in 32 bits. But the reason we use FP8 is to store it in the memory, in GPU memory in FP8, and to move it faster into DRAM. So data moving, data bandwidth, and data storage. That's what we use that's what we use FP8 for. And when we do the calculations, the dot product, we first convert it to 32 bits before we calculate, before we do the dot product. And we keep the results and everything accumulated all in 32 bits. So storage movement of data FP8, calculations FP32. I will mention a couple of times that calculations are done in FP8, but that's not true. I just realized that later. By the way, you can also always ask AI to explain to you everything I'm saying. And also the value of watching this video is that you learn what questions to ask. Even if you don't understand fully what I'm saying, now you know what what questions you need to ask and what you need to understand. Okay, as I said, we need to first calculate this scale factor. So by what do we need to divide this largest number to get this largest number here, 448. So in this case, we are dividing it by about, I don't know, 2.15 or something. So this is how we get this scale factor here. We divide the largest number by the 448, we get the scale factor. In our example, we have this block and this block. These lines are not well represented by ChatGPT, but okay. So these two blocks, so we divide the largest number here, and this is the scale factor, and the largest number in the other block, and this is the scale factor. Now that we have scale factor, we need to make, we will just divide entire block by the scale factor. So this will scale the entire block so that the largest number is 448, and all of the other numbers are gonna get scaled accordingly to keep their relative values, relative magnitudes, relatively same, relative to each other. So that means if you have a big number, if your largest number is bigger than 448, then every number will get smaller. But if your largest number is smaller than 448, then when you divide by this scale factor, here, every number, you will get bigger numbers for each element. And as I said, the largest number will always be 448 because you are just reversing this operation here that you did. So anyways, this will zoom in or zoom out the numbers. So it will. So now the reason you're doing this is, as I explained, you want to use the entire range of FP8 to represent numbers. So they are as well distinguished between each other as possible. Now, interesting thing about representing in FP8, you cannot represent every single number, not even every single integer between these two values. Because you remember the formula, you need to have you are multiplying by powers of 2 basically, so not every number integer is representable. So ChatGPT here says, let's presume it's correct, but if it's not correct, even if ChatGPT made a mistake, I don't know, doesn't matter. My point is you cannot represent every number, every integer. So if you get, like, for example, number 5, you would maybe represent it as number 4, as the closest representable integer here. So you would just save it as into memory as number 4, even if it's number 5, because that's the closest thing you can represent. Now, you can also represent some decimal numbers. So you will basically round up to the closest number that you can represent in FP8. So let's say we have some number 5.53. We cannot represent this number in FP8. There is not enough exponent and mantissa bits, so we need to round it to the closest number, either up or down, the closest number. So these are some calculations. It says like it's gonna be rounded to 5.5 because that's the closest number. So we will save into memory, into FP8, this number instead. But for neural networks, it doesn't matter. It's close enough, it's precise enough, so we can have a lot of memory savings, a lot of save this into FP8 instead of FP16 with minimal accuracy losses. And when I say neural networks and memory, I mean the matrix multiplication can be done in FP8, but then gradient accumulation and other steps are actually done in FP16. So we just do the matrix multiplication to make it faster in FP8. To return to our example, we are calculating these numbers in the array, scaling them. So we scale the original number with the scale value. We get to 22.4, but this number will get rounded to 22. Other numbers are accidentally can be represented according to ChatGPT, so we will trust it. So we get the quantized quantized vector, and then we get the scale. So we need these scales to later, after the matrix multiplication, convert these quantized numbers from FP8 to FP16 or FP32, whatever we need it for. So basically we will use these numbers to do the matrix multiplication, which will be a lot 2 times faster in FP8, and then go back to FP16 after. So we will store our tensor in the type that I explained earlier, float 8, exponent 4, mantissa 3, finite only, and scales will be stored in float 32 because we need to have them precisely stored. You see here these numbers. I don't think it would be possible to represent them in float 8, and they would just be rounded to 0, so we would lose our scales. But you see, entire block gets one scale in a float 32, and one block in DeepSeek has 128 elements. So now we are just storing one instead of 128 elements in float 32, or those elements would be in float 16. And after we do matrix multiplications with these float 8 numbers, then we can dequantize later. So we get our y block, so each block, or this could be like result block, if we are doing multiplication or whatever, times scale, we get the dequantized block. So the calculations are shown here is the same. So the values are gonna be almost exactly the same, with a bit of error because of rounding, because when we were converting to FP8, we couldn't represent all of the numbers, so we had to round to the closest one. But this is completely tolerable for LLMs. So we have a local dynamic range. That just means that instead of using same scale for entire tensor and coming up with issues, the scale not properly fitting all of the range, we instead divide it into blocks, and for each block we have a scale. So it's going to, that's why they call it dynamic range. So it's like calculated for each block. Guys, my bad. The computation is happening in 32 bits. So the movement of data is happening in 8 bits. You see, storage on the GPU and moving to DRAM happens in 8 bits. And then it gets converted. We have this to float 32. It gets converted to 32 bits just before the multiplication, the dot product. And then, so computation and accumulation in 32 bits. So that will be it for this video. Thank you for watching, and see you in the next one.